Hello, this is part 2 of network epidemiology. So now let's talk about a few elements involved in um, eh, mathematical models of epidemics in population with structure. So first we have one of the conveniences of the compartmental models of infectious diseases is that the compartments are quite intuitive and they are related to what we call epidemic states or epidemiological states. So in those equations, each box represents a subgroup or subpopulation, and they are dubbed or named after the state, epidemiological state in which individuals are found. In a basic model with three compartments, typically one of the compartments denotes individuals that are susceptible to infection. The other compartment, the one that is usually denoted with the letter R, stand for recovered individuals. And the compartment in the middle are those that are, and here is where there is there's several words used. Those individuals are called infected. They're also referred as infective. But here in this type of representation, which is a cartoon of a real world scenario, in this type of representation, it is assumed that individuals become infected and immediately have the capability of passing on infection. And that capability is known as infectiousness or being infectious. There are certain diseases that have intermediate states or states you can think of as incubation or latency states or stages, and so they may be infected, not yet infectious. But in this representation with three compartments, the middle compartment with letter I typically represents and assumes they are ready to pass on the pathogen. So with this representation, we may consider several events. The main events include some events that are demographic in the sense of new arrivals into the population and then departures from the population. It is standard to assume that the new arrivals are born as susceptible individuals, and it's also possible to assume mortality, but only due to natural causes. And these will be translated into having some rate of departure, the same rate of departure from every compartment. But the events on this representation, some of the specific events related to the epidemic are the transition from the epidemic states. So going from susceptible into infected is called an infection, an event of infection, and then moving away from infection means that the immune system of the individual is able to fight off the infection, and eventually the individual is no longer infectious and develops immunity and therefore become recovered. Some of these events and these transitions between states are going to be determined by functions that will depend on time and space, and these functions are denoting or functions taking values between 0 and 1, and they denote the likelihood or chance for every vertex representing each vertex represent an individual, the likelihood that every vertex will switch between states, and here the space is determined by the structure in the population. That's what is being referred here as space. So the space is referring to precisely this type of representation of space where each vertex it has a way of getting there are edges, there's a number of edges, and then there is a sense of paths in this space represented by this network, and the network is the set of vertices and edges that defines it. So these are important definitions. The probabilities are then both time dependent and also they depend on the structure of the population. So here's an example. There are two nodes, each of them labeled with a number. So there is vertex 1, which is in the current state of being susceptible, and there is vertex 2, which is in the current state of being infected. There is nothing connecting, there's no edge between vertex 1 and 2. So we would say that the probability of the vertex 1 or node 1 to become infected is equal to 0. There is no way in which this node would inherit infection. However, if the scenario allows, if we consider this other scenario in which node 1 is connected to node 2 by an edge, then and is the only connection node 1 has, then we would say that the probability that node 1 becomes infected is equal to 1. So these are illustrations of the two extreme values that the probability may take. And so what we point out is that when a particular vertex or particular node will have several neighbors, and all the neighbors are the other nodes and the other vertices that are connected to the one node in reference. So when a node has multiple nodes or vertices that are connected to it, then the probability of infection will be proportional to the number of neighbors that are in the infected state. And since this state of infection also varies and changes with time, then that will induce to having probabilities that are depending on the time step and also are dependent on the state of the vertices or the state of neighbors. So a very basic epidemic model for structured populations would be one model in which the network is assumed to remain on the same shape throughout the time scale of the epidemic. So, and that is what is considered. There is this word here, static network. Is a graph that doesn't change its given configuration. So every node has also a fixed set of contacts, a fixed degree. And so if that is the case, if we have a static network and in which every node has the same degree, then the probability of transmission from one infected vertex to a susceptible vertex along a given edge or entire duration of infection is given by this ratio, where beta here denotes the rate of infection across an edge, and where 1 over gamma denotes the average duration of time that an individual may remain infected. It is very typical to assume that this average duration of infectiousness is a random variable that is exponentially distributed. So if this is not always going to be the case in which the graph will necessarily have the same degree for all nodes, but is a point of departure. So there are definitions of the basic reproductive number in terms of populations with this, where the structure is addressed or is modeled with networks. The definition in words is the same as we had seen before: the average number of secondary infections caused by a typical infective individual when introduced into a population that's assumed to be entirely susceptible. And when we have the scenario in which all vertices have the same number of degree, which here we denote with the letter K, then the basic reproductive number is that probability we mentioned before multiplied by this number, which is the degree minus 1. So that's degree of all nodes. So in a way, k minus 1 is denoting the number of contacts, or is quantifying the number of contacts across the graph, and that number of contacts is corrected by the probability of infection, and it's a little smaller than the number of the degree. But in other types of graphs where it is known that the degree is not always the same for all individuals, and in fact where there are strong levels of variability on the degree of vertices, then the estimate for the basic reproductive number takes this form, in which this part here looks very similar to the part that we had before, that k with that symbol that denotes now the average degree in the network, and then there is other quantity that denotes the variance. So if you may recall from statistics, the average is the first moment, the variance is the second moment, and here the degree is considered a random variable. So you may also recall that this ratio here has a name in statistics, or this ratio may be related to some particular quantity in statistics. So to refresh your memory, you may look up at the definition of what in statistics is called a coefficient of variation. Okay, and that coefficient of variation is something that relates both first and second moment. So the basic reproductive number in this way takes into account the average connectivity, or the average degree. The first moment of degree takes into account the variability on the connectivities, and it also takes into account that probability of infection between nodes across an edge. And that this is an estimate, a known fact that happens for a specific class of networks that are considered heterogeneous, that are considered to have a heterogeneous degree distribution. And one example of such type of networks has to do with the networks that are called scale-free. So a model for network growth by Barabasi and Albert is an example of the type of networks with these heterogeneities on the number of connections, or the connectivity distribution.